Anyway, welcome to Daytona Beach, Florida. Is this a wonderful place or is this a wonderful place?
It's Reno.
Oh, God. Huh. Did they announce last night where the next symposium is going to be? I was hoping here, yeah, but someone said there was a possibility that Houston was going to jump in there, and I said, wait a minute, it's supposed to be 2 times in the same place. I figure if it's in Houston, this is my last symposium. If it's in Daytona Beach, I'll have one more. Okay. Any aeronautical engineers in here? All right, we got him. Yes, he's my watcher. He takes check on me. I'm not an engineer. I'm a parachute designer, but in doing so, I've got a lot of engineering studies behind me. Today we're going to look at compatibility question. We're going to look at 2 sides of compatibility. Component compatibility, the physical, legal, moral requirements of component compatibility, and we're going to talk about the duties of riggers. Riggers inspect, pack, and certify parachutes for emergency use. Riggers are responsible for component compatibility. There is a section in AC 105 that says any question, when you mix or match approved components, any question about the function or safety or operation of those should be resolved by actual tests. Okay? 2 areas of compatibility are functional and structural. In the past, all we've had to worry about was volumetric considerations, and then we got the deal with weights and speeds and placarding forces, so we had to worry about structural considerations. And now we've got, or maybe we don't, we've got some concerns about functional considerations that we have to learn more about. The ability to calculate the functional compatibility is something we're going to have to expand our horizons to. Future will require more knowledge. In the future, more knowledge will be required for riggers to make necessary determinations. Today, the first section will look about functional compatibility. In order to do so, we'll look a little bit at atmospheric sciences, dynamic pressure, pilot chute drag capabilities, and container extraction effort. The second section will be the second hour, depending on how fast I go, will be structural component requirements. And we'll expand our learning in that section to include opening force models. That's math models. Math isn't hard, folks. It's really easy. Mary, didn't you get an A degree?
A what degree?
Aeronautical engineering degree?
No, I got a biological degree.
Oh, okay. You're more biological than aeronautical? Okay.
My sister is the engineer.
That's it. That was it. I knew that one of your all's. Folks, this is Phil Getch, D60. His wife, 65, sorry. Jamie Stoyas was 60. His wife, Carol, they got more jumps than God. Phil is one of my mentors. And I thank you. Today we'll review some history of regulation and discuss the legal and moral requirements. By the way, resource access. Anything I talk about is published, and it's published on my website. If you go to the Parachute Labs or Jump Shack website, there's a part called Technical Articles. For the last 25 years, ever since we've had an internet, we have had a policy that if we have a question or investigation of some sort, of some minuscule aspect of parachute equipment, we do the study and we write a paper. And we publish the paper in those technical articles. So there's a tremendous amount of information in there, especially for newbies that come along and have these same old dumb questions that we've all answered many, many times. Additionally, these are the links for it. Additionally, I've written documents to try to stimulate the sport to move in certain directions. I've written a document called A Case for Compatibility with Functional Integrity and A Case for Compatibility with Structural Integrity. And those are basically what this class today is, first half, second half, functional and structural. Recently wrote one, Why 18 pounds should be the maximum reserve free bag extraction force. And we'll go into that a little bit later. I did find out last night from England that Sunpath has accepted a 32-pound extraction force on a Javelin Odyssey, acknowledging that it's acceptable but on the high side. My math tells me that at 32 pounds of extraction force, you can't pass the TSO test. 18 pounds the most you can have and pass the TSO test as far as I'm talking about 3 seconds, 300 feet TSO test. 32 pounds is excessive. Quite frankly, most of those folks don't know how to calculate what you're going to learn how to calculate today. Okay, the other thing, I've already posted on my website a spreadsheet which has dynamic pressure, Q, by altitude and speed. It's there. If you want to go to the download section of my website, you can download it as an Excel spreadsheet, so then you can manipulate it. But it has row built into it. It's a lookup table. We'll see more about it in a minute. We may be able to get it to come up for us. Functional compatibility. Do we have a functional compatibility problem? Let me ask you this. Do you know the drag capability of your reserve pilot chute? Anybody that knows the drag capability of their reserve pilot chute, raise your hand. Wow. Wow. Is that a problem? How much force does it take to extract the reserve bag from the container? Anybody know that? And most of us are riggers. How many are riggers here? Okay. This is what we got to do. We got to measure that extraction force. We can't measure the pilot chute. We're going to see more about that as we go on. But you got to check that extraction force. That rig comes in for a repack. You pull that bag out by that bridle. It's the easiest way you can pull it out. Measure it. If it exceeds 18 pounds, pack the rig, seal it, pull the ripcord, and measure it again. If it's still exceeding 18 pounds, and 18 pounds is an arbitrary number, and I will get into the development of that number later, call the manufacturer. He'll say, send it back. He'll send it back. He'll pack it and say it's okay and pass it out. We've seen that happen. Dave DeWolf did one. He called me on the phone. He says, I got one I packed. I thought it was tight, so I opened it and I spun the rig around with the main full and closed. And by the way, that's the way they should all be tested. Not spinning them around, but with the main closed and full. Better for the fish scale than spinning. Spinning's more of a show stunt until we learn to use a fish scale. He said, I could spin it around my head. So I called the vendor, the manufacturer.
You have a video of that? Because I'd like to see old Dave DeWolf trying to spin something.
Unfortunately, he was naked, so they, no, Dave didn't get a video, and he just called me on the phone and told me about it. He sent it back to the vendor, and I'm not telling you who the manufacturer is. And sure enough, the manufacturer said, it's okay. Yes?
Some people mentioned that the whole direction of the pilot chute when free fall is 90 degrees to the sample of spinning around your head, because this is upwards. They say, well, it should really explain.
Those are people who think flat and stable is the only way to pull. I disagree with that. I think stable is the way to pull, but I think flat is a bad idea. You should be rotating around your shoulders, keep your shoulders level with the ground. Phil taught me that. Keep your shoulders level with the ground, and that way it keeps your lines even, and you rotate and sit up in your opening. Do not pull flat and stable. You can, but get out of there really quick, get vertical. And so I disagree with what you're saying. I got called on this. I put a video, there is a video out of the spin. Somebody called me on it. And they said, that's not the way you get a bag out of a container. And I said, shit, I've been doing it wrong all these years. 40,000 racers, and they'll all come out in that direction. They all should come out in that direction. I said, I've been doing it wrong. Whew, no, that's wrong. Anyway, what are the limits? How do we measure? If we don't know, then there's a problem. If we don't know, then there is a problem, and here's the proof. Let's see if we can make this work. Here's some of those videos. Let's see. There's a mouse.
Other button.
All right, here you go. Look at this pilot chute. That's a reserve pilot chute and a free bag bridle. Do we have a problem? How about this guy? Has he got a problem? That's a full main.
On the ground?
How about this guy? This is a NASA wind tunnel test of a pilot chute. Now notice the oscillation of the pilot chute. It's high frequency and low amplitude. That's the way a drogue drags. That's an indicative of it not doing it. And here's some fat old man trying to spin one of these around. The wolf couldn't do it, but this fat old man could do it. Now notice when the leg straps finally hit the ground, next time around, I think, hit over by the pilot chute, it torques and the bag twists out. Okay? So I ask you, do we have a problem? Before I go any further, are there any British people here? Golly, my other class didn't have any Brits either. They don't need to come. They're smart. I'm serious. I have here in my hand the paper that the British Parachute Association is adopting this weekend. It's called Reserve Opening Procedures. Purpose, to monitor the opening performance of reserve systems at the end of the repack cycle, providing valuable information, helping maintain packing standards, and identify the reasoning for any poor performance found. We expect the reserve system to operate effectively even when deployed at low speeds and low altitudes. Although exactly what these limits are is subject to some speculation. We also expect the reserve pilot chute to clear any burble and be able to extract the free bag even if the main is still in the container and the flaps are securely closed. We also expect the length of the time the reserve has been packed to have no adverse effect on deployment performance. They have methods, they have a picture of how to do it, and kudos to the BPA. Shame on USPA and PIA. They've had this problem for 3 years. I spent 2 hours last Friday in a tech committee meeting, which has the responsibility for this issue. The agenda for the tech committee had TS-100, TS-133, and free bag extraction effort listed as number 3. The tech committee, 7 canopy manufacturers and 5 harness and container manufacturers, sat there for 2 hours and discussed ram air parachute nomenclature. The free bag committee, after 3 years, never has reported it out and has done nothing. Nothing. Some USPA official the other day told me, oh, USPA is just wringing their hands because they can't get anything done. If you knew what USPA did to settle down the river, this problem when it first arose, it raised its ugly head. And I give USPA credit for investigating this problem and really bringing it to light by doing a database study and finding 9 similar occurrences to what we had this past weekend. We had this terrible tragedy in Zephyr Hills. But that problem in Zephyr Hills, trust me, is the tip of the iceberg. This is a pervasive problem. I have a friend who I met here for the first time who is a East Bloc, former East Bloc citizen who has learned English very well and migrated to our society, and who's a professional parachute rigger at a major European drop zone. When he first saw that spin test, he thought it was a setup. I met this guy on the internet. I finally got to meet him here. He's extremely sharp. He says, I thought that was a setup, so I went and got one, and I found out it wasn't a setup. I couldn't get the bag out. He then started testing everything he tested. Now, I intentionally stayed away with naming types of rigs. I'm not here to sell my rig. Okay, I'm here to tell you that there is a problem, to tell you how to solve the problem and how to help the sport get out of it. Our organizations won't help us. It's up to us, the riggers, to solve this problem. We're the people whose name was on that card when that dude's in the ground, his AAD's fired and his reserve didn't come out. Now, the one in Zephyr Hills, the report from TK Hayes is that everything's fine. There's nothing wrong with the equipment. Go on down the road, folks. The world's okay. If there's nothing wrong with the equipment, then what happened? There's something wrong somewhere. Somebody's dead. 2 guys are dead. 2 different rigs, a J3 and an Icon. And the AADs fired almost simultaneously. We'll get the rest of the AAD information pretty soon, and we'll get more information about it. Anyway, back to the problem. Congratulations to the BPA. Shame on USPA and PIA. Riggers to the rescue. Properties of the atmosphere. Static pressure. We got 2 kinds of pressure in the world: static pressure, dynamic pressure. Static pressure is actually defined by rho, which is determining the density of air in slugs per cubic foot, all of which change with altitude. Now, this is the first page of the 4th chapter of Theo Konecki's Design Recovery Guide. It's a book this thick. It's the size of a pointer's manual. It's no longer in print. If you want a copy, go to my website, download section. You'll see Design Recovery Guide. It's 15 meg or something, but you're welcome to have it. I was going to read from this page and get a lot of my information from it, but the writing is a little bit small, a little bit tight and hard to read. It does tell us about static pressure, density of air, but we're going to talk about that anyway here. Two types of pressure, static and dynamic. Static pressure is pressure which is not moving. Now, I get called on ambient pressure being equal to static pressure, and they're technically right. So we'll just forget ambient, we'll talk about static. Dynamic pressure is static pressure. I said ambient here, but I mean static, with the addition of velocity. So we've got static pressure and dynamic pressure, and the only difference too is dynamic has velocity. We've talked about the pressure inside the wing of a ram air, and people think that it's a ram air, that the pressure inside the cell is greater. And the reality is it isn't. It's static. It's whatever the pressure is. The pressure on the outside is reduced, and that's what makes the cell expand and gives you the pressure differential. But there's no movement of air inside the cell, so it can't be dynamic. It can't be anything greater than static. Okay, remember, air is a non-compressible liquid. As far as we're concerned, I still believe that to be true. We've had some discussions about it the past couple of days. Dynamic pressure. The mathematical term for dynamic pressure is Q. You know, you've heard the space shuttle take off and roger roll, Houston, what's your Q? You ever hear that? I have. Made me feel good. I knew what it was. You know, Q is dynamic pressure in pounds per square feet. It's based on altitude and speed. The faster you go, the higher the Q and the lower the altitude, because the air is denser closer to the ground. Expressed in pounds per square foot. So the formula that we're going to look at for developing dynamic pressure, which is the fundamental atmospheric phenomena that we skydive on. When we skydive, we're at 33 pounds per square foot. Works out about right. If you've got 6 square feet of body surface and you weigh 180 pounds, that's about 30 pounds per foot. That's equalized, or what we call terminal velocity. Okay, Q, 1 in pounds per square foot, PSF, equals 1/2 rho, the density of air, times velocity in feet per second squared. Rho is the density of air in slugs per cubic foot adjusted for altitude, velocity is feet per second. We need to know this dynamic pressure, or this Q, in order to calculate drag. And that's where we're going. We're going to learn how to calculate drag for a pilot chute. This is the chart that's available on my website that tells us what the dynamic pressure is. Unfortunately, the chart goes way out to the right, and way out on the end is rho. We've looked it up and put it in, and it's a lookup chart from Excel spreadsheet. And you can see here, did I get a laser pointer? Yeah, here. Right here, at 20 feet per second, this is not speed per second miles per hour. Speed across the top, altitude down the bottom, all the way up to 27,000 feet. 20 feet per second is a malfunction, okay, by definition. So if you're at 2,000 feet and you've got a malfunction, a minimum malfunction, you've got 0.45 pounds per square foot to work with. You better have a big pilot chute. Okay, we're going to need a bigger boat. So, I'm going to pass on from this chart. And by the way, as you go on up the line, you can take this chart and take that 2,000 feet, go on over here. Oh, I go a little faster here at 33 feet per second. I'm up to 1.25 pounds. Well, if I get to 67, which is going to happen in about 3 seconds, I'll be at 5.11 pounds per square foot. I keep going. I'll get enough pressure to pull that bag out eventually. But I'll hit the ground first. That's why it has a 300-foot limit, folks. Drag, components of drag. Q, dynamic pressure in pounds per square foot. It's the one we just talked about. We all understand Q, dynamic pressure. It's so significant. The SO, and sometimes this is just S, and sometimes it's S sub P, but it's the planform area of the device in square foot. As far as a pilot chute goes, it's usually a 36-inch diameter flat circle. Okay? The CD, the C sub D, drag coefficient. Physicists call it the C sub X, or some call it the C sub O, but it is the drag coefficient. It's one of those things that turns a wag, which is a wild-ass guess, into a swag, which is a scientific wild-ass guess. Okay? It really means, for those of us who are laymen, it means the percent efficiency of that shape. So we've got a 36-inch device, and we know that when we put air on it and it bends and folds, it's not going to drag 36 inches worth. It's going to be reduced substantially by the shape, and that CD compensates that. And what those two together give us, CD and SO, is the effective size. In other words, it drags like. okay? It may be 7 feet, as a matter of fact, 36 inches in diameter calculates out to 7.06 square feet. I didn't do that in my head, I've done it a million times, that's why I know it off the top of my head. And if the CD is 0.83, then you got 5.92 effective square feet out of the 7 available. Now, there are those that will argue about drag coefficient a little step further. If you had a flat plate, a rigid flat plate, and put it in a wind tunnel, you could actually get a CD of greater than 1. Because as the air wraps around that plate, it effectively enlarges it. That was a stunning thing for me. I learned in my first session at the University of Minnesota in the Aerodynamic Decelerator Systems Conference. Blew me away. I said, geez, that's interesting. We had wind tunnel stuff in colored smoke and stuff. Anyway, the CDSO represents the effective size. The effective size is the number that you guys are going to get to work with eventually. Currently, all of my pilot chutes are placarded with the effective size that they have. Okay, and I want, my goal here is to get every pilot chute in the industry placarded to that. I have proposed to PIA to build a world tower so that the members can test their damn pilot chutes. Okay, effective size, CDSO of the pilot chute is required to be able to calculate the total drag for a given altitude of speed, of airspeed, Q. Effective size must be placarded. Effective size times dynamic pressure, Q, is equal to drag. Do you know the CD? How do you know the CD? Because that's a number we haven't discussed yet, an element we haven't discussed. The only way to know it is to measure it. You've got to put it in a wind tunnel or whirl tower. You don't want to take it into free fall because the oscillation of a good pilot chute will break your arm. A good pilot chute is going to be so violent in its oscillation, it's going to be like playing tug with a bull mastiff. If you know what I mean, you know it's going to be. I went to Russia in '92, and we were developing our tandem system. While I was there, my wife, my erstwhile wife, what a woman. Anyway, she gets the tandem system, grabs this dude from the drop zone, little Josh, and they go up and test a drogue. Chooses a 24-inch pilot chute that we had at the time. The smallest thing we had was a spring load. And we got video of it. And that drogue out there, you know, that bridle, Nancy and Josh down here, and it was whoa, 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 like this all over the sky. And they went through about 5 or 6 gyrations of that. And I said, we gotta get out of here. And then pulled and released it and deployed okay and got away. But the violence of it is what I was talking about. We just saw that video of that pilot chute, reserve pilot chute in tow. That thing's sitting up thinking, dee-dee-dum, dee-dee-dum, dee-dee-dum. That thing should have been chucking him all over the sky. Anyway, so the only way we know a CD is to measure it. We take the same formula we just learned, which was drag equals CDSO, and we reverse it, solve for CD. So that's drag that we measure divided by the SOQ. Well, we know the square footage and we know the Q because we can measure it in the tunnel. So that'll give us the drag coefficient. Measurements are usually done in a wind tunnel. A cheaper alternative might be a whirl tower. And as I say, this is the one from China Lake. I saw this picture and I said, geez, we don't have to have a one like that to test pilot chutes. You can get one the size of a little kid's merry-go-round. Because all we got to go is 20 feet per second. And you can make a circle 20 feet with a 4-foot arm and get 60 RPMs, and you're doing 20 feet a second. So I made a proposal to PIA, and they took it favorably. I don't go to their meetings. I go to the tech committee meeting only. And they like the idea, and it is an alternative for them. I think they're going to have to do it. Okay, drag and oscillation. We've talked so far about the technical aspects of drag. Now, what's it look like? We've talked about that a little bit. We saw the video. Oscillation has 2 characteristics, frequency and amplitude. How fast? How far? Okay? Drogues have low drag, high frequency, low amplitude, and low oscillation. All drogues, tandem drogues, sit up there and go like this. Just vibrate. You can barely see it, but that's what they do. They vibrate. Okay, pilot chutes don't do that because we don't load them. If you load a pilot chute, it's going to start oscillating like we talked violently. But pilot chutes never get a chance to get loaded because we put them out there, they anchor, and we pull away from them, and then they turn inside out, and we go on down the road. We don't get a chance to drag them at overspeed. So pilot chutes don't oscillate until they are loaded and in tow. I have had several questions about the Mon Premier Reserve, the bag, the deployment you saw here, that say, well, I've got a base pilot chute that doesn't oscillate. Of course it doesn't. You don't put it in tow. So people don't understand that. Some guy wrote last night, a fairly experienced instructor from Zephyr Hills, they're all on the shed about raising hell about this Zephyr Hills accident. And he said, well, I know thousands of soldiers that have thousands of jumps on round parachutes that don't oscillate. I had to laugh. One of the characteristics identified on round parachutes in the scientific literature for each parachute is the angle of oscillation. That's the whole thing about round parachutes. They oscillate. We cut holes in them so we could make them steerable and so they wouldn't oscillate. It was more so they wouldn't oscillate. My first canopy was a 28 flat with a single blank gore. You couldn't even change views with it, but it didn't oscillate, you know? Okay. Now, here's a video of NASA Ames wind tunnel test. This is a high drag pilot chute. If you'll notice, the pilot chute keeps going out of frame as it's violently oscillating. So it even has, you can see the blurred edges shows you the speed or the frequency of it. And this thing is just, this is an angry dog right here, okay? An angry dog. And notice how he goes past the edge of the door. We're filming through a window here. And this is back in '89, by the way, that we did this. And this whole exercise that I'm talking about here today, we did back in '89. We studied this back then. We made sure our ducks were in a row. Now here's another kind of pilot chute. You may recognize it by the big round hole in the bottom. It's all that's dragging. Notice it has a high frequency and a low amplitude. Okay? It's dragging like a drogue. The designer of it calls it a balut. A balut is a supersonic drogue. A balut doesn't drag until you go to supersonic speeds. This pilot chute has a 0.33 drag coefficient. It has a 2.3 effective square footage. Okay? Now, I've taken the same video that we've just been enjoying here and slowed it down by 20%, slowed it down to 20%. It's going to be the same exact video slowed down. It may take longer to run. But it gives you an opportunity to see how far out of frame each one of these oscillations is. This is the good high drag pilot chute. And here's the other one, and you can see it barely gets to the edge of frame in any time. And these are tested at the same speeds. We're looking at about 30 Q. Okay, so now we understand drag, the components of drag, and how they're developed. To review, Q is the mathematical designation for dynamic pressure, which was 1/2 rho times velocity in feet per second squared. SO is the planform square footage. CD is the drag coefficient or percentage of efficiency. The visual characteristics of drag are oscillation, which have two features, frequency and amplitude. Frequency is based on speed, amplitude, and my favorite term, spill and fill. Low amplitude, low drag, high amplitude, high drag. The other half of the equation, container bag extraction effort. How do you measure the effort it takes to extract the bag from the container? As I mentioned earlier. With some disdain, PI has been studying the problem, trying to determine all the different directions from which the bridle could be pulled. They told me that, and I said, what an exercise in futility. How absurd. They've been working on it for 2 years, and I said when I prepared this thing that they were expected to report out here at this meeting, which we did, and they didn't. They now have 3 years that they've been working on it, and it has never been discussed in the open meetings because when USPA handed this problem down to PIA, and PIA assigned it to the tech committee, I reactivated myself and started going to tech committee meetings. I've been to every one since. And I have challenged the tech committee to poll the manufacturers to see what their maximum bag extraction efforts are. They know better than to admit it. They know better, folks. Okay, I say pull it in the direction creating the least resistance. with the main full and closed. That's real important. When we're investigating this problem, some rigs are suspect and are in violation when only when the main is full and closed. Some other rigs will fail, it doesn't matter. I find the ones with the bad pilot chutes seem to fail more with the main open. However, they all have that problem. Now, the trough riser covers, someone brought up the other day, the trough, which are the riser covers that are part of the side flaps of the main container, those trough riser covers prevent the rig from bending, which is something I've always favored. And we've developed a trough riser cover system for the racer back in 2000. And I was very cognizant of how those trough covers work. And it concerned me a great deal because I knew back then that they had the ability to make the reserve extraction effort higher. And so we did a lot of work with trimming down the upper corners of those riser covers. And we also went back in and reshaped our free bag by making it rounded at the corners and having we always have had the V, the apron at the top of it, which is a V, which helps it out of the container. But we even rounded the corners to make sure there were no sharp corners to get caught up in there. And we've never had a problem with it. We also measured the force, and we knew at that time what our pilot chute would do. As a matter of fact, we were using, when the racer was originally designed, we used an MA1, which is a drag coefficient of 0.65 or effective square footage of 4.62. So we based everything on that. Our current pilot chute is considerably better than that. We got lucky and copied Ted Strong, and the pilot chute came out good. So anyway, we want to give the manufacturers the benefit of the doubt, because if you pull that bag out any other way than the way it's the easiest resistance, they're going to have something to say about it. They're going to say, that's the wrong direction that you pulled it, you know? So you pull it out in the easiest direction. Because let me tell you, they won't get away with anything when you do that. How much extraction force is allowable? This is where it gets tricky and where we have to use our own intelligence. Depends on the capability of the pilot chute and exactly what dynamic pressure it occurs. If it's at a cutaway we're looking at, then we've got less force available to us. But certainly extraction force is greater than the drag of the pilot chute, you have a failure. So what can a pilot chute drag? Well, that's why you got to know the effective square footage, because then you can apply that to the dynamic pressure of that situation, that speed and altitude. Okay, practical consideration, a reason for the 18 pounds. We based the 18 pounds on the racer pilot chute, the racer 36-inch pilot chute. Now I've listed here what do the best pilot chutes do. I got an MA1 at 36-inch, a 0.65 CD, and I was going to let the class calculate that. Well, I printed up here really small letters, 4.6 square feet. Racer 36-inch, 0.84, 5.92 square feet. Vector 1, 36-inch pilot chute, 0.79 CD, 5.58 square foot. A hell of a good pilot chute. I tested it at the NASA tunnel at the same time I tested the Vector 2. Notice the Vector 2 pilot chute is not up there. And we gave Mr. Booth the results of those tests, and he studied them for 3 days. And he came back at the end of 3 days and announced that this just proves that you can't test a pilot chute in a wind tunnel. I've never shared information with him since. Container volume considerations. Do not overstuff a reserve container. Check the canopy's volume against the placarded container capacity. Most manufacturers provide recommended sizing information. Use it, don't go over it. It's not a good rigger who can pack a brick. It's a dumb rigger. Good Lord, I had 2 guys who used to work for me, and they'd get an order from somebody and they would intentionally size the container one size smaller so it'd be tight. Good, they thought. These racers have wrinkles for a reason. Racers are made to fit human bodies, not tables. There is a container which will always look bad when overstuffed. Name it. Of course, it's a racer. You overstuff a racer, it looks like hell, but it'll still work. Structural consideration. This is the second hour of the class. How are we doing for time, folks? What time is it?
35 minutes.
It is 35 after?
Yep.
I mean, I did that first half in 35 minutes. It's supposed to take me an hour.
And we didn't give you enough shit.
You're not giving me enough shit, that's
I'm
right.
too tired to argue.
All right, if you want to take a short little break, we can, or we can forge right on through this thing and finish the whole thing in less than an hour, probably. That's kind of up to you. We've lost one, he's disgusted. Anyway, I'll go on, I don't mind. Just soon do it. It's the last day, we all want to go home soon, but we do need to cover this. Remember drag? We just talked about it. Remember the formula? Drag is equal to CDSOQ. Drag is in pounds. It doesn't have to be drag. We could substitute the word pounds in there. Or we could substitute the word force. So we'll take that formula and add two new components and make it a force formula. Introducing Mr. X1 and the CX factor. They're the two new components that we add to the drag formula to make this an opening shock math model. The first factor is the X1 is a decreasing load factor, and this was the most enlightening thing that I ran into in studying this kind of thing. This chart is from the Kaneki Recovery System Design Guidebook, and it is a chart which makes figuring the X1 or decreasing load factor easy. See, force reduction factor he calls it here, opening force reduction factor versus canopy loading. This formula, Fx, let's call that pounds, we had it drag, was CDSO times Q times CX X1. Well, we know this first half here is the drag formula, and we're introducing the X1 in a minute. We're going to talk about CX, but X1 is a very interesting factor. It is the factor that takes in consideration your weight and your pound per square foot loading. Notice here, if I had a 2-to-1 pound per square foot loading, I would come up here to this point and pick this number, which would be 0.2. Well, that's interesting. That's 1/10. I just moved the decimal point, so I can do that. Go back here to 1-to-1, come up, and we're at 0.1. So let's go way down here at 0.4. Well, look, we're at 0.4. So effectively, in this range, all the way up to about 2.5, 3-to-1, and we don't ever load much more than that, we're at 1/10 of the pound per square foot loading. We don't even need that chart. We can do that in our head. The stuff you get up here in this end of the chart is for bigger parachutes and other